structures. We're going to be doing Lewis structures till like Thanksgiving. So make sure you learn them because we're going to be drawing them until Thanksgiving. So make sure you've got your Lewis structures down. Okay. So what we're going to do now is we're going to use those Lewis structures and we're going to use them to figure out how molecules are structured. So how molecules are structured, that's what we're going to be doing for the next week or so. And then we're actually going to do a lab on this too. It's called VSEPR theory. And so VSEPR theory is called valence shell electron pair repulsion theory, VSEPR for short. And really it's based on the fact that electrons are negatively charged. And remember Coulomb's law, like the lowest energy, right? Like charges repel. That's pretty much what VSEPR is based on. They want to get as far away from each other as possible. That's VSEPR theory. And we use the arrangement to predict their shapes and bond angles. And from there, we predict how they behave. So for example, if you had, I don't know, think of it like 3 balloons. And you know how if you ever take when you were a kid and you took a balloon and you like rub it on your head and it gets all like it gets all staticky, right? If you did that with 3 balloons and you put the balloons next to each other, they would repel into what looks like a triangle, right? That's kind of what VSEPR is talking about, how the electron groups repel each other. So first of all, we need to talk about what an electron group is and how we use it. So the Lewis structure predicts the number of valence electrons around the central atom. So anything around the central atom, we call an electron group. And it doesn't matter if it's a single, double, or triple bond, or even a lone pair. So for example, when we see this molecule right here, so this is what your homework is on this week, is drawing these Lewis structures. So you got to be able to draw this Lewis structure. But when we look at electron groups, we're always looking at the central atom. And again, when you're looking at your Chem 101 this week, when it says like how many, like for example, the question was how many lone pairs or how many electrons are around the central atom? Well, there's only 2 electrons around the central atom. When we talk about the central atom, we're only talking about this. Now, electron groups are things that are attached to our central atom. So what's attached to our central atom? 1 electron group. So we would call this like a bonded atom. Another electron group or another bonded atom, and a lone pair, and we would just call this one Ne. And so this nitrogen has 3 electron groups around it, a lone pair, an oxygen, another oxygen. We don't care if it's a double bond. We don't care. We don't care if it's a lone pair. It's just the number of things around the atom, 3 electron groups. 2 of them happen to be atoms. 1 of them happens to be a lone pair. So now we're going to learn about the geometry. And you're going to learn, I'm going to teach you how you're going to have to learn all this geometry. And unfortunately, you kind of have to memorize it. It's going to become sort of important. Okay, so the linear electron geometry. So if we have 2 electron groups and we try to attach them, our electron groups are going to try to be as far away from each other as they can. And so for here's BeCl2. So here's 1 electron group, 2 electron groups. Here's CO2, 1 electron groups, 2 electron groups. So we call this linear. And so if we call our central atom A, and we call, this is A, and this is B, and B, we call this A, B, 2. Or if we do this here, if we call this A, here's a bonded atom B, here's a bonded atom B, we call this AB2. Any atom that has the structure AB2 is going to be linear in geometry, meaning it looks like a line. The bond angle in between these atoms is 180 degrees, right? It makes a 180-degree bond angle. So AB2, or sometimes we call it, instead of a B, we call it X. It doesn't matter. I call it B because it's a bonded atom, but whichever one of those works. So again, so here's a linear geometry. and a bond angle is 180 degrees. Now the next one, here's boron. So our boron is going to be BF3. So we did our Lewis structures last one, right? This is 3, 7 times 3 of them, right? So that's going to be 24. We draw our skeleton structure, subtract the ones we've used, and then we 2, 4, 6, 8, 10, 12, 14, 16, 18. And remember, boron is an exception to the rule, so it only has 6. And if we check, we've got 24, right? So that's how this is what we did last time. So if you're unsure about how to draw Lewis structures, make sure you go back to the lecture, or I also have some supplemental lectures on drawing Lewis structures that you watch those, because that's the key to the whole entire next month is drawing Lewis structures. Now, trigonal planar geometry. So even though we drew it like this, right? This is how we drew it. If we look at the number of electron groups, so here's our middle atom, I'm just gonna call it A. Here's one bonded atom, B, another bonded atom, B, another bonded atom, B. So you see how we drew it here with a 90-degree angle here? That's how we drew it, but that's not how it actually is. It actually ends up being 120 degrees, right? Think of it if you had those like 3 negatively charged balloons. They would try to repel each other. The furthest they can get away is 120 degrees. They look like a triangle. That's the furthest they can get away from each other. So even though we draw our Lewis structure like this, it doesn't mean that's the correct shape of the Lewis structure. The correct shape looks more like a Y. And when you draw these in Chem 101, it's going to automatically put it into the correct shape for you. So you get used to doing this. Also, on Tuesday in lab, we are also going to be doing Lewis structures, figuring out the shapes. So we're going to get to play with a bunch of models. It'll be fun. Okay, so this is central atom A, 3 bonded atoms. So we would call this A, B, 3. The geometry is called trigonal planar. The bond angle is 120 degrees. So again, our central atom we're going to call A. This is a B for bonded atom. This is a B for bonded atom. This is a B for bonded atom. So we call this A, B, 3 trigonal planar, and the bond angle is 120 degrees. So any structure that has this format, a central atom and 3 bonded atoms, is called trigonal planar, and its bond angles are 120 degrees. All right, now let's look at what's called tetrahedral. So if you've got 4 electron groups, it looks like, do you know like the bottom of a music stand? You know how it's just like the music stand and then the 3 prongs at the bottom? That's kind of what tetrahedral looks like. And on Tuesday in lab, we'll actually see this. And so CF4 would be an example of a tetrahedral. So again, here's our A, our middle atom. There's 1 bonded atom, 2 bonded atoms, 3 bonded atoms, 4 bonded atoms. So this is A, B, 4. So if we were, for example, to draw CH4, it's supposed to be an H, it would have the exact same molecular geometry of AB4, and its bond angles are 109.5. And I try to get a way to make it so you can see this, but it's kind of difficult. It looks like, again, kind of like, so like here's the music stand and there's like the 3 pieces of the music stand. I can't draw. Let me try again. So like that's the bottom of the music stand and that's the top. And like, so this is coming like out towards you, right? That's sort of what it looks like. And it's called tetrahedral 109.5. And again, on Tuesday, we get to play with all these and we're going to make these shapes with our Lewis structures. We have these little balls and sticks, like Tinker Toys on Tuesday. Okay, so Trigonal bipyramidal. Okay, so when there's 5 electron groups around the central atom, they're going to occupy positions that are both tetrahedral and what we call axial and equatorial. So we call this trigonal bipyramidal. Oh, someone had a great question. Is there an equation to know the degrees, or you just have to memorize it? You just have to memorize it. But I'll teach you. It's actually, I have a nice little cheat sheet that's on your Canvas for you. That's really going to help you with these. So the positions above and below are called axial, and the ones that are in the same plane are called equatorial. And the bond angles between the equatorial are 120, and the bond angle between the axial are 90. Okay, so I'm going to try and show you what this means. So see, you know, like the equator goes around the globe. So these are like the equator, the ones that go around. I can't draw a circle, but they're going around like in a circle like that. Those ones are 120. And then the ones that are like this, these are a bond angle of 90. And this is called trigonal bipyramidal. So for example, here's PCl5. So again, PCl5 is an exception to the rule. It can have an expanded octet. And so when we draw it, we might draw it like this, but that doesn't mean that's the actual shape, right? Here we have 3, and again, these are like in the same plane, kind of like if you had like a circle, or if you had like a piece of paper, they would all be the same piece of paper, right? And then the others are above and below the piece of paper. Let me see if I can try and draw this. Hold on. See if I can try and draw this. Hold on a second. Every time I hold anything to my camera, everything disappears. So I'm trying to find something that doesn't disappear when I hold it to my camera. So it's gonna, oh, look at, I got this one staying. Okay, so these C's right here, they would be like in the line of this little black piece of onyx I have. These Cls, one would be above it and one would be below it. So you've got these 3 that are around it here. They're 120 degrees apart from each other. So these guys are 120. The one above, you can see that makes a 90-degree angle right here. The one below, again, makes a 90-degree angle between those two. And so it has both 90 and 120 degrees. Now, if we look at this generic shape, is we just call the middle A, and then we call this B, and 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 we call this B, because they're all bonded atoms. That's A, B, 5. So whenever we have a structure that has the same kind of thing with one atom in the middle and 3 atoms around it, it's AB5 trigonal bipyramidal. Its bond angles are 90 and 120. Here's me again trying to make it so you can see it, but it's a little difficult. Okay, next one, octahedral. Okay. So octahedral is going to have 6 sides to it, or 6 things to it. It looks like it looks kind of like a pyramid, sort of, when you look at it. It's like a square pyramid. I'm going to show you what a picture of this looks like. The bond angles are all 90 degrees in an octahedral geometry. So for example, everything is 90 degrees away from each other in an octahedral. This one doesn't show it very well. So like here, here's our atoms. They're all at the edges here. And so they're all 90 degrees away from each other. This kind of shows it a little bit better, So here's the ones that are, so you have these guys that are kind of on this circle, but they're 90 degrees away from each other. Because think of it, if you had like 4 negative things around a circle, the furthest they can get away from each other is 90 degrees. And then the one above it is also 90 degrees, and the one below is also 90 degrees. So in octahedral, everything's 90 degrees. If we look at the generic form of this, here's our A, which is just our generic middle atom, B, 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 B. This is A, B, 6 octahedral. And the bond angles are 90 degrees. And here's what it looks like. Here's me trying it again. Okay, trying. Okay, now everything we've done so far is only bonded atoms. But what about if there's lone pairs on our central atom? They occupy space. So lone pairs are literally negative charges, right? So they're going to occupy space. So for example, here's our Lewis structure. So we might draw it like this, right? But again, just because we draw it like this doesn't mean that's the actual way, that's actual bond angles. Right? This is going to be, let's just do our little structure here. This is A, B, B, B. This is A, B, 3. Remember, AB3 is trigonal planar. And we said the bond angle was 120 degrees. Now you see how it's not exactly 120 degrees, but it's close to 120 degrees, right? Because they're not all the same. Remember, if they're all the same atom, they have the exact same electronegativities, right? So they're pushing exactly the same. But if they're not the same atoms, they have a little bit different because oxygen is more electronegative, so it can repel the other atoms better, right? Because negative charges repel. But we can just say it's a little less than 120. Do you have to memorize these? No, no. Writing a little less than is perfectly fine. Okay, so how do we know the difference in these bond angles? So let's look. So the effect of these lone pairs. So lone pairs are going to occupy more space because their electron density is exclusively on the central atom rather than being shared. So it's going to have a much better ability to repel the other atoms in the structure. So how do we know the difference? So the greatest repulsion is going to be 2 lone pairs. So we call it lone pair, lone pair. The next one is lone pair, bonding pair, and then bonding pair, bonding pair. And we're going to talk about what this means in just a second. Show you an example. So this makes the bond angles smaller than we expected. Okay, so let's look at, so bonding pair is what we were doing. So let's look at one of these, a lone pair and a bonding pair and how it affects the bond angles. So if we draw the structure NH3, so this is NH3. Hopefully we're all good with drawing the structures, right? If not, make sure you watch that video. So here's NH3. And so you can see there are 1, 2, 3, 4 things around our central atom. So we would write this, right? A, B, this is a B, this is a B, and this is a B. But this is an electron pair. So A, B, 3, E. There's still 4 things. So we would think, oh, 4 things around the central atom, that's 109.5, right? Because we had AB4 tetrahedral, AB4 tetrahedral. That was like the music stand one. We said the bond angles were 109.5. But when we add this lone pair, the lone pair is like, get away, get away, get away. And so it's pushing the other atoms closer to each other. So instead of being 109, they're actually closer to 107 because the lone pairs are taking up more space. So when we have an AB3E, there's still 1, 2, 3, 4 things, but since one of them is now an E, the bond angle is just less than 109.5. Do you have to remember? No, just less than is perfectly fine way to know this. Less than. Okay, so that was a lone pair bonding pair. Let's look at a bonding pair. So remember, if there's all atoms, we said it was 109.5. If we have one electron pair here, we said it's less than 109.5. Let's look at this one. So here's water. So here's the Lewis structure for water. So if we look here, this is our A. Our A. And again, we have 1, 2, 3, 4 things around our A, but 2 of them, this is a B, this is a B, B2, lone pair, E2. So there's still 4 things. So we would think, oh, 4 things, that's 109.5. But again, even though we drew the structure like this, right? People draw this and they're like, oh, it's linear. Well, just because you drew it linear doesn't mean it is linear, right? It actually is a tetrahedral shape, right? That music stand shape. But instead of the bond angle being 109.5, because now we've got 2 lone pairs that are even pushing further, and these lone pairs are like, we don't want to be by each other either. They're shrinking this bond angle. So instead of 109.5, it actually ends up being like 104.5. So how do we do this? Do you need to memorize this? No. I just say less than 109.5, like much less than 109.5. So if we have 4 atoms, it's 109.5. But if we have 1 lone pair, it's a little bit less than 109.5. If we have 2 lone pairs, it's a bunch less than 109.5. Or really just knowing that it's less than, that's all we really need to know, is that the lone pairs make it less than 109.5 because they're pushing the atoms together because they're repelling each other. Okay, so we have different names because these shapes are a little bit different, right? So when we have, let's just do this Lewis structure really quickly just to review Lewis structures. We're gonna do, I'm just gonna do this over here. This is gonna be SO2, and I know you can see this in your notes, but I wanna review again, just Lewis structures for those of you that we're all working on our Chem 101. So remember, if we do a Lewis structure, this is 6 times 2. Oops, that'll just be a plus sign. This is 18 valence electrons. So we draw it as symmetrically as we can with the least electronegative atom in the middle. So that's a sulfur. Oh, sorry. We've used 4 electrons. So that means we have 14 electrons left. We add them as lone pairs. 2, 4, 6, 8, 10, 12, 14. Okay. Now remember, we added 14. We can't do this because the maximum we can have is 18. This structure has 18 valence electrons. Can't have more than 18. Can't have less than 18. At this point, when we check for octets, oxygen is good. Oxygen is good. Sulfur only has 6. Again, we can't add. We can only rearrange. So we take one from here and we make a double bond. Now we still have 18 valence electrons, so we're good. Oxygen has 8, oxygen has 8, sulfur has 8. This is our Lewis structure. So if we look at this Lewis structure, this is our central atom. This is A, B, B, E. So this is A, B, 2, E. So we call this bent, right? And again, here's those resonance structures that we could draw. These 2 would be minimized according to octets. This one would be minimized according to formal charges, right? So this is the difference between the 2. Octets versus formal charges. Okay, we call this AB2E when we have 2 atoms and a lone pair. And its bond angle is just less than 120. less than 120. Okay, now let's look at more of these. So we have a tetrahedral that looks like it's bent. We're going to look at it in a second. And when we have a pyramidal that also looks like a bent. So let's look at these two. It's easier, I think, to see it than the words. We'll come back to the words. Okay, so if we have the structure, right? This is A, B, 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 B. This is A, B, 4, tetrahedral, 109.5, right? But if we look at our NH3, this is A, B, 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 E, A, B, 3, E. This is pyramidal. So the shape is called pyramidal, or we call it trigonal pyramidal. You'll see why in a little. Trigonal pyramidal, and its bond angle is just less than 109.5. Now let's look at another one. Here's another one. Look, here's our A, B, 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 E. There's another one, A, B, 3, E. So whenever we see A, B, 3, E, we think trigonal pyramidal or just pyramidal. Bond angle, less than 109.5. So for the bond angles, it's not really that difficult to remember them, because if you just remember, if there's 4 things around it, so if you remember that there's 4 things around it, it's 109.5. If one of those happens to be a lone pair, it's just less than 109.5. If 2 of them happen to be lone pairs, it's just extra less than 109.5. So here's another one. Here's A, B, B, E, E. So this is A, B, 2, E, 2. Now, this one is called bent. We just call it bent. Sometimes we call it tetrahedral bent, and I'll talk about that in a second why. So if we had 4 things, it's 109.5. But we have 2 lone pairs. So again, less than 109.5. So it's ABE2 bent. And again, I'm going to show you something in just a minute that'll really help you put all this together in one piece. All right, let's look at this one. Here's our A, B, B, E, E. So A, B, 2, E, 2, bent, less than 109.5. Right? And again, 109.5, because still 4 things. That's where we get that bond angle. And we say it's less than 109.5. Okay, now these next ones we're going to talk about are a little more tricky. When we get into lab, they'll make more sense. Okay, so we're going to look at a seesaw, which literally looks like a teeter-totter, and then T-shaped, and then linear. And these are all variations on trigonal bipyramidal, which means they have five things attached to them. Okay, so if we, I'm gonna go back to red. I feel like red is easier to see on here. If we have A, B, 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 and then here's an E. So this is A, B, 4, E, right? This one, the bond angles, we just kind of discard. We're like, I'm not really talk about these bond angles, right? And so this is our trigonal bipyramidal. This is what we do with this one. And so we call this seesaw. This is why. It looks like a teeter-totter. Like, see, this is like the bottom of the teeter-totter, and here's the people sitting on top of the teeter-totter. Right, from when you're a kid, like it's sitting on a seesaw going up and down. It literally looks like a seesaw. And so this one is A, B, 4. I can't drop my B's fast enough. And there's your E. So this is A, B, 4, E, and it's called seesaw, right? So this is called seesaw. We literally call it seesaw. The next one is called T-shaped. And so if we look at this, here's our A, B, 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 E, E. So it's an A with 3 B's and 2 E's. This is called trigonal bipyramidal. That's the electron geometry because there's 5. But because we have the lone pairs, it actually looks more like a T. So so trigonal bipyramidal, that's what we call the electron geometry. That's AB5. But the actual molecular geometry, meaning the shape of the molecules, this is a 90 and a 90. It literally looks like a T. We call this T-shaped. And I know right now it's just a lot of like, whoa, how am I gonna learn all these things? But it gets a little easier once I give you the little handout. So again, here's our A. And the reason I keep doing this with the B's is because this is going to be the way you're gonna figure out the shapes in an easier way. E, E, A, B, 3, E, 2, T-shaped. The next one is linear. And the linear one, you don't even really need to remember, because if you have one atom and there are 2 atoms attached, the only way those atoms can be is linear. So I don't even worry about this one, but if we want to do this one, it would be, that's our A, B, B, there's 1 E, 2 E, 3 E. So this is A, B, 2, E, 3, linear. Whenever you see 2 atoms attached to one thing, it's always linear no matter what. So these electron pairs here, what they do is now the electron pairs are located here on this little disk, and the atoms are one up here and one down here. So the electron pairs are in a circle around this disk. And so the atoms are 90 degrees or 180 degrees away from each other. Okay, we only have one more, octahedral. Octahedral, remember, was 6 things. So when we have 6 electron groups, we're gonna either have square pyramidal or square planar. All right, so octahedral means 6 things, right? But if we have one lone pair, that's our E, B, 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 B. There's our A. So that's A, B, 5, E, right? That's going to be called square pyramidal. And so it looks like, so that's like the bottom of the square. And then this is like a pyramid, which I think we all know by now that I cannot draw. Oh, hi, I kind of made a pyramid there, right? It's called square pyramidal. Really, that's how bad of a drawer I'm. That's actually a really impressive drawing for me. We call it square pyramidal. And for these bond angles, when they get these complex bond angles, we're not even going to talk about those bond angles. We're just going to do the simple bond angles. All right, let's look at this one. A, last one, B, 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 and then there's an E here and an E here. So this is A, B, 4, E, 2. This is called square planar because they're on a square. And so here, the atoms are on this disk, right? They're 90 degrees away from each other on the disk. And then up here and up here are the lone pairs. And that's going to make a big difference in our next module. But right now, we just need to figure out where they are. So our whole goal right now, by the way, is we're trying to figure out why atoms behave the way they do. But in order to figure out how they behave, we have to figure out their shapes, because their shapes determine their behavior. Okay, so how do we do all the things I just showed you? Number one, draw the Lewis structure. This is what your homework is this week. It's really long. I apologize, but if you're not good at Lewis structures, then the second exam and the third exam go awful for you. So Lewis structures are literally the key. So we really need to get good at Lewis structures. So I apologize for the long homework this week. Then we determine the number of electron groups, and we count them as either bonding or lone pair. That's what I was doing every single time I drew a Lewis structure right now, because I wanted you to get used to doing that yourselves. And remember, it doesn't matter if it's a single, double, or triple bond. A bonded atom is a bonded atom is a bonded atom. And then you use the table to determine the shapes. Okay, so let me show you the table I have made. I didn't actually make this. When I was in grad school, one of my professors made this, and it was so good, I stole it. So I'm going to show you where this table is right now. Let me just share my screen. Sorry, my computer's going crazy right now. Oh, I don't think I put this on your canvas. Oh, I did, but it's in a different module. So let me just show you. I'm going to put it in the module here, but here it is. I'm going to copy this to the module we're on. Actually, I'm just going to make a copy. Sorry, my internet is like, as you can see, it's not working. Anyway, I'm going to put this in the module so you can see it, but here's the molecular geometry sheet. And I have this later in the lecture also. And all of these extra things you'll see will mean something. There's extra pieces on here right now. So here, let me just write on this. So here, instead of X, I used B in the lecture. So this would be B2, and then this would just be AB2, so AB2. Let me just go down to let's do this one right here. You're going to learn how to use this very, very well. So here's this one. So this would be, here's tetrahedral. Remember, tetrahedral is, here's B and E. So this would be A, B, 4. And again, see how I used an X here instead of a B? This would be A, B, 3, and then 1 E. And again, I used an X, but that's trigonal pyramidal. Here's A, B2, E2. And again, I used X's. And it is bent. And so it's kind of like everything right there. And then here's a little example molecule that goes with them. And then here's a picture of what the shape looks like. And then here's the bond angle. And remember, every time we have an electron pair, so this would just be less than 109.5. This would just be much less than 109.5. Right? Oh, so can you use it on your exams or quizzes? I don't know. We'll have to see. Maybe on your first quiz, but I don't think you can use it on your exam. I think the other professors might be really upset. Okay. Usually you have to memorize this, and I'm going to teach you how to memorize it. I have these really awesome flashcards that I'll get you if you want to help you memorize these. It's kind of a lot, but this again, it will be on your Canvas page. Right now, it's under. This is going to take forever if I go back. It's in the next module. Just going to take a minute for my Canvas to go back because my computer and Zoom are such good friends. So right now, it's right here, molecular geometry sheet. I'm going to put it in the next module too, but it's just taking, my computer won't do it right now. I'll put it up here. I'll put it right up here in this module also. So this will teach, and we're going to use that a bunch. So you're going to see how to use that in the next 2 weeks. All right, you guys can see this now. Okay, so we're gonna practice. And I'm gonna try and I'm gonna go back to that so you can see. Okay, so here it is, PCl3. We're gonna go back and forth on this. Okay, so for PCl3, first we draw the Lewis structure. So I want you on your papers right now. So if you're watching this now or watching this later, draw the Lewis structure for PCl3. Because again, I think you're seeing that if you don't know how to do the Lewis structures really well, then you literally can't do the rest of it. And the whole half of the second exam is on this. And the third exam has Lewis structures on it too. So we really need to get good at Lewis structures. So draw this Lewis structure now, and then we're gonna keep going in just a minute. So draw this now. While I pull up, and I'm going to put this geometry sheet here on your PowerPoint while you do that. So draw this Lewis structure now. And then we're just to prove to yourself that you can. Let me know when you're done with your Lewis structure. All right, are you ready? Yes, okay. I'm just putting this sheet in here for you so you can see it. Okay, so PCl3. You look at our valence electrons, right? Phosphorus is 5, fluorine is 7. There's 3 of them. Add this up, 26 valence electrons, right? So then we put P in the middle, and we put it as symmetrically as we can. So 3 Cls. Again, just because we draw it this way doesn't mean this is what the actual shape is, right? So we've used 6. That means we have 20 left. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Then we check, do we still have 26? Okay, I'm gonna do this in a different color. This check part is the one that people always skip. This is the most important part. Don't skip this part. Let's do octets first. Fluorine has 8, fluorine has 8, chlorine has 8, phosphorus has 8. Okay, octets, good. Now, Let's look. Do we still have 26? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Yes. Okay. Structure check. Those last two pieces are absolutely the most important part of this of Lewis structures. Don't skip those. Okay. So we've decided our Lewis structure is P Cl with, looks like this, right? I know my dots are not very good right here. So if we do our little A's and our B's, I'll do it green. So here's A, B, 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 E. So this is A, B, 3, E. Okay, so we have 4 things around it. So we look at this and we decided again, it was A, B, 3, E. And so there's 4 things around it. So we go over here, total number of electron groups, there's 4. There's 4 total things around it. And then we look for, here's our B's. Again, I call them X's here, but actually I didn't, make it tired it. But here, these are B's and these are E's. So we look for 3 B's and 1 E. 3, 1. The shape is trigonal pyramidal, right? The shape is trigonal pyramidal. And the bond angles, because there's a lone pair, would just be less than 109.5. Okay, so that's how we use this little sheet. Oops. So again, 4 electron groups, 3 B's, 1 E, makes trigonal bipyramidal, bond angles less than 109.5. And again, you don't need to remember them, you just need to remember less than. And no, this chart is not allowed on the exam. But when you're doing your homework, this is how you use it, and then I'm going to teach you how you can memorize it later. So yeah, you're going to have to know all these. But for your homework, this is how you use them, and then you get better at it. Okay, so I want you guys to try this one. And I put this chart on here, but this is going to test your Lewis structure skills, because this was SIF5-. We did one like this one on our last lecture. And then I want you to figure out what is the molecular geometry. So even if you're watching this later, super important, try this now, because a lot of times when I do the structures, you're like, oh yeah, I can do that. And then you're like, that's not, I can do that. And then when you're doing it on your own and you're doing homework, you're like, what? I don't understand. Why can't I get this right? Do this now, so then whatever mistakes you make, we can correct right now, and you can fix it while we're doing the lecture. So try this now. I'm going to pause it. I'm going to shut my video off for a couple minutes. So try this now and see if you can get to the correct molecular geometry for this structure. And then we'll go over it in just a couple minutes. Okay, I'm seeing a bunch of them. Let's see. Let's try. I don't have any room to write this because I put the structure where I would usually have room. So SI5 minus, I'm going to try to do it. Oh, actually, oh, just there. Okay, so let's look at this one. SI5 minus. Okay, so SI goes in the middle because it's a least electronegative, right? So we're going to put that one in our middle, and then that'll be our central atom. And then we add our, I'm just going to do this up here. We add our valence electrons, right? So SI is, where's SI? 4. That does not look like a 4. F is 7. And there's 5 of them. And remember, this means add 1, add an electron, right? So we get a total of 40 valence electrons. And so we draw our SI in the middle, and we just put 5 Fs around it. Really, how you put the Fs around it is kind of like, you just do your best. Like, so this is going to be an expanded octet, which can happen. We've used 10. That means we've got 30 electrons left. Okay. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 6, 28, 30. The better you get at these, the more you're going to rush, and then you're going to end up having to count by 2 twice. So just don't rush. Okay, so now we got to check for our octets. Does F have 8? Yes, 8, 8, 8, 8. And S has 10, so we're totally good with our octets there. So that means our structure is good. And do we still have 40? We count again. Yes, we find out we have 40. Okay, then, so blue. This would be our A is our central atom. And then we have B, 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 A, B, 5, right? So we look, A, B, 5. Okay, so again, when we do this, there's 5 total things around the central atom, right? We got 5 things, 5 electron groups. They happen to all be bonded atoms. So we're at 5. So we look at this and we go to 5. And then we have, again, AB5, which means 5 bonded atoms. So here's, or if we look here again, on this one it's X, but X is B. So this is trigonal bipyramidal. If I ask the bond angles, you would just say 120 and 90. I didn't ask the bond angles here, but that is how we do it. So also, I want to show you one thing. We'll really talk about this more when we get to in lab, but because there's a negative here, it's a little like side note. Because there's this negative here, we need to show that this is also negative. So we put that around the edge. So that'll come up in Chem 101 sometimes. Don't forget to go, if there's a negative or positive, if you had a positive here, by the way, that would be like subtract an electron versus add an electron. But we have to show that it's a negative, otherwise it makes our valence electrons off. So those are structure, which sort of, I tried to make it not overlap, but it overlapped. Yeah, Hector, do you have a question?
Yes, I had a similar encounter with this, and I couldn't put the parentheses around, so I got it wrong.
Hold on a second, I can't hear you. Let me turn up my speaker. Can you say that again?
So I had a similar encounter with this problem. I think I couldn't put the parentheses in there on the Chem 101, and I got it wrong.
Oh, so there should be a way for you to put the parentheses in Chem 101. Maybe that's a formatting thing. I'll look at it right after we finish this. We'll go to Chem 101 and do one of these with the parentheses. Yeah. Let's see here. Why does this become S in the Lewis structure? Eric, you're gonna have to ask that question again. I don't exactly understand it. I see it, but I don't understand. Oh, why does SI become, Oh, that's just because I forgot to put the I. It doesn't. I just, yeah, so question, why did I change it to S? I didn't, I meant it should be SI. Thank you. Yeah, that would have probably confused some people, so thank you. Yeah, it should be SI, not S. Okay, and again, I'll look at the Chem 101 so we make sure that we put these negatives around here because this happens in Chem 101. Okay, so let me just, so 5 electron groups, 5 bonding pairs, 0 trigonal bipyramidal. The bond angles are 120 and 90. And I'm not going to say like which bond angles. If you just say 120 and 90, that's fine. That's totally fine. Okay, one more. So this is really going to test your Lewis structure abilities here. So I want you to do ClO2F. And again, if you're watching this now or if you're watching this later, this is really going to help you with your Chem 101, right? So try this one, and then we want to know what the molecular geometry and the bond angles are. I'm going to give you a couple minutes, and then we're going to go over this together. So even if you're watching this later or you're watching it now, I know I can't see you, but trust me, try this because it's going to make your life so much easier later if you get good at these now. So try this, and then we'll go over it in just a couple minutes. Okay, so I'm seeing a few of these. All right, so we have ClOF2. So the first decision we have to make is who goes in the middle, right? Somebody goes in the middle here. So it's Cl, O, or F. Remember, the least electronegative element is going to go in the middle. So chlorine will go in the middle. So chlorine's going to go in the middle. Let's just do our valence electrons real fast. Right, so our chlorine's in the middle. So chlorine has 7. And sometimes people think it's a C and I. It's that can be tricky. I'm not gonna lie. So it's 7. I'll try and always tell you that. 6 times 2, and then F is also 7. So that's 26 valence electrons, right? So if chlorine goes in the middle, O, O, F. I mean, you kind of draw it. You just put 3 around it, right? Just because we draw it like this doesn't mean it actually is. So we just draw it like this. We've used 6. So this gives us 20. So 22, a lot of counting by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18. I feel like I was reading the chat and didn't count these right. Let me do this again. This is 20, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I was like, see when you get distracted? This is why I say when I say I'm like, don't rush counting by 2s, because then you just end up having to do it twice, just like I did. I ended up having to do it twice. And then we have to check. Does everyone have 8? Yes, 8. Yes, 8. Yes, 8. Then we check, does chlorine have 8? Not meant to erase that one. Yes, it has 8. Okay, so F. The question was like, does the first one, yeah, usually they write the least electronegative element first, but not always, but usually. Like, for example, if you have like HCN, well, H definitely doesn't go in the middle, all right? So usually the least electronegative element goes first, but not always. So usually this one is in the center, but not always. So always check least electronegative in the middle. Okay. All right. So let's see here. We're good. Checked our octets. Check. Do we have 26? Again, most important part, octets. Do you have the number that you're supposed to have, right? Okay. So if we look here, we have 26. We're just going to say, yes, we've got 26. Okay. Let's check what we've got. So you see how the Lewis structure is so important? Because if your Lewis structure is wrong, then your shape is wrong, and then your bond angle is wrong, right? And so we have here, this is going to be A, B, 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 E, A, B, 3, E, right? A, B, 3, E. And then we look at our little cheat sheet, all right? And we say there's 4 total things, right? Everyone agrees there's 1, 2, 3, 4 total electron groups. So we look at our cheat sheet here, and we look for the 4, and we decided it was A, B, 3, E. So that means 3 atoms, 1 electron pair, 3 atoms, 1 electron pair. This is trigonal pyramidal. Bond angle less than 109.5, right? Less than 109.5. So here it is. Let me just erase mine so you can see all this in summary. So do we see how the bond angles are the Lewis structures are super important, because the Lewis structures lead us to the correct shape. The shape is what's going to lead us to the behavior, right? And so someone had a question, how do you know when you use double or triple bonds? Well, let's do one with double or triple bonds. Let's do HCO. I'm just in my brain going, which ones do I know have double and triple bonds? So if we do, let's do H, that one will work better. Yeah, let's do this one, H2CO. So try that Lewis structure. So this will be our last thing we do today. Try this Lewis structure, and then we're gonna get to double and triple bonds. So we're gonna go over this one in just a minute, and I wanna know what is the shape of this. So what's the molecular geometry or the shape of this one? H2CO. Last one we'll try, and then we'll go over this together in just a minute. Okay, let's try this one. So this is 2, 4, 6, right? So 12. C is going to go in the middle. O, H, H. C goes in the middle, least electronegative. So we've used 6. So we've got 6 left, right? Did I add that right? I just do this consistently. 1 times 2 equals 12, right? So we use 6, so we have 2, 4, 6. I feel like I've done something wrong here. I can add. See? All right. So when we do this one, we've got 2, 4, 6, 8, 10, 12. Well, this one's not quite working with our carbon and our, probably took the wrong structure. I was trying to make one that would make it be a double bond, and in my brain it didn't work as a double bond. This one isn't going to work right. I'm going to change the structure here just to make it easier. So let's do HCO. That one's not going to work with our Lewis structure. We'll just leave this Lewis structure as in. It's not going to be exactly the correct Lewis structure with the C's. H. It's hard to do these in my head. O. right? Yeah, the double bond should be right here. So this is what it should end up like in the end. Sorry, I know we're almost done. So this is what the Lewis structure should look like in the end. Now, when we do it, this is our A, B, 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 A, B, 3. And I know, I'm sorry, I'm going over time. This is trigonal planar. Right, and so this is going to be, oh, I should have done it in a different color. This is AB, sorry, AB3. You can read that, AB3 trigonal planar. And again, it doesn't matter if it's going to be a double or triple bond. So sorry, I ran out of time to talk about it. But if you do the lone pairs and they don't work, then that's when you have to make the double and triple bonds, right? Okay. All right, so that's all we have time for today. I don't want to, oh, it's a really quick question. So this is still a B, even though it's a double bond, it's still a B. These are still B's here. Doesn't matter if it's a double or a triple or a single bond, they're all the same, right? So it doesn't matter. So this could have been a triple bond, still a B, right? Or a single bond, a B, double bond, still a B. Doesn't matter the bonding, it just matters that it's an atom attached, right? If there had been a lone pair here, then we'd have our E. So the only distinction we make is atom or a lone pair. Okay, so again, sorry I went over a little bit.